In this video, we will talk about the reliability failure patterns, the studies around them, and how these failure patterns align with the choice of the appropriate maintenance strategies. Reliability failure patterns refer to how the probability of failure changes over the lifespan of the system. Understanding these reliability failure patterns is crucial for developing effective maintenance strategies, optimizing system lifespan, and ensuring the safety and reliability of critical systems over time. Proactive maintenance practices, continuous monitoring, and technological advancements contribute to managing and mitigating the impact of age-related and random-related reliability patterns in various industries, including aviation, manufacturing, and infrastructure. Before the 1960s, maintenance practices were often based on fixed overhauls and predefined maintenance schedules. This approach, commonly known as time-based or scheduled maintenance, involved regularly overhauling and inspecting components and systems at predetermined intervals, regardless of their actual condition. The idea was to prevent failures and ensure the reliability of equipment through routine, periodic maintenance. Various studies on equipment failure patterns have been conducted over the years, and they have significantly contributed to the development of maintenance strategies and reliability engineering. Here's a brief overview of some of the mentioned studies. United Airlines conducted a landmark study in the late 1960s, known as the United Airlines Maintenance Steering Group (MSG) program. This study aimed to optimize maintenance practices and move away from fixed-interval overhauls. The U.S. Navy has been a pioneer in the development and application of reliability-centered maintenance. The Navy's efforts, particularly in the 1970s and 1980s, contributed to the widespread adoption of RCM principles in various sectors. The Bromberg study, conducted in the 1960s, was led by Stanley Bromberg. The study focused on the relationship between equipment reliability and maintenance strategies in the aerospace industry. Finally, John Nolan and Stanley Heap played key roles in the development and popularization of reliability-centered maintenance as a systematic and structured approach to maintenance decision-making. The conclusion of these research has shown that most failure modes are not age-related. In fact, less than 20% of failure patterns are age-related, and more than 80% of failure patterns are random-related. These findings contradict the belief that there is always a connection between reliability and operating age. This belief led to the idea that the more often an item is overhauled, the less likely it is to fail. Nowadays, this is seldom true. Unless there is a dominant age-related failure mode, age limits do little or nothing to improve the reliability of complex items. Moreover, scheduled overhauls can actually increase overall failure rates by introducing defects that will cause infant mortality into otherwise stable systems. There are 6 reliability failure patterns. Among the age-related failure patterns, we have Pattern A, the bathtub curve. The bathtub curve failure pattern begins with a high incidence of failure, known as infant mortality, followed by a constant or gradually increasing conditional probability of failure, and then by a wear-out zone. This pattern encompasses approximately 4% of all failures patterns. Pattern B, known as conditional wear with wear-out phase, is an age-related pattern showing constant or slowly increasing conditional probability of failure, ending in a wear-out zone. This pattern encompasses approximately 2% of all failures patterns. The last age-related pattern is Pattern C, known as constant wear or fatigue. Pattern C shows an increasing conditional probability of failure, but there is no identifiable wear-out age. This pattern accounts for approximately 5% of all. Among the random-related failure patterns, we have the Pattern D, break-in curve, also known as best new curve or rapid increase to random. It shows low conditional probability of failure when the item is new or has just been refurbished, then a rapid increase to a constant level. This pattern accounts for approximately 7% of all failures patterns. Pattern E is a random failure pattern, showing a constant conditional probability of failure at all ages. This pattern encompasses approximately 14% of all failures patterns. Finally, pattern F, known as infant mortality curve, starts with high infant mortality, which drops eventually to a constant or very slowly increasing conditional probability of failure. This type of failure accounts for 68% of component failures. In conclusion, these studies collectively contributed to the evolution of maintenance philosophies, moving away from traditional time-based maintenance to more proactive and cost-effective approaches like RCM. Reliability-centered maintenance involves analyzing the functions, failure modes, and consequences of failure for each component to determine the most appropriate maintenance strategy, whether it be corrective, preventive, or predictive maintenance. The principles of RCM have been widely adopted in various industries, including aviation, manufacturing, and other critical infrastructure sectors. RCM has proven to be effective in improving equipment reliability, reducing maintenance costs, and enhancing overall system performance. The evolution toward more sophisticated and data-driven maintenance strategies has been a continuous process, with ongoing research and practical applications shaping the field of reliability engineering.